And let me introduce our next speaker.
Thank you.
Professor Rolf Binder from, I'm sorry, it's University of Arizona or Arizona University?
Yeah, this is the University of Arizona. Let me open my.
Always were very angry on me when I call it a different way, but I still missed in these two institutions.
I don't know. I hope you can see the logo here. This is the University of Arizona, and Robert Kindle is at the Arizona State University, which is the bigger. The ASU is much bigger than the University of Arizona actually, and it's in the capital of Arizona in Phoenix basically, whereas we are in the south in Tucson.
Thank you very much. So please.
All right. Well, thank you very much, Mike. And I also want to thank Mike Grafilov and Jim and Jason for organizing this great conference under the most difficult circumstances, really. So in a way, my talk will continue on the theme that was set up by Robert Kindle in the previous talk. We are also interested in terahertz spectroscopy, and we are also interested in using that spectroscopy to probe systems with symmetry breaking. But we are not looking at interesting new materials as Robert is. We are just looking at semiconductor microcavity lasers, so at an all-optical system, basically. The people who did all the work basically are here, Matt Spotnitz, my graduate student, and my colleague, Mike Wong. So I want to give a little bit of background first on polaritonic states in particular. Sorry, I forget to, let me try to get the laser pointer here. A little bit of background on polaritonic states, in particular BCS states, Bardeen-Cooper-Schrieffer states, and then I will lay out in more detail our theory of terahertz absorption in lasers. I call them here photon lasers. I say in a minute why, and I will present our numerical results that we did for gallium arsenide microcavity lasers. So let me start with a background. I don't think really I have to talk about polaritons here in this conference, but I do it anyway just for completeness. So we start out with electron-hole pairs in the semiconductor. Of course, they can, in principle, form excitons due to the Coulomb interaction. These excitons then can be in, say, a quantum well, could also be a 2D material, but in our case, it's a quantum well. Which is between two mirrors, like a regular laser, basically. And so the excitons, they can move in the quantum well with a certain in-plane wave vector, which I call K here. And the dispersion of the excitons is just proportional to the inverse mass of the exciton. But on a relatively small scale, the dispersion is really rather flat, as shown here. We also have the cavity modes, the light modes in the cavity. They have this minimum here, and the minimum corresponds to just the standing wave in the cavity. And so if we couple these two modes, then we get the well-known polariton branches. We are in particular mostly interested in the lower polariton branch shown here, which has been used in many fundamental studies, including demonstrating polaritonic Bose-Einstein condensates. So I want to try to put this work a little bit more into context. And so the context is basically we are interested in macroscopic quantum effects and spontaneous symmetry breaking in these microcavities. And the keywords that come up immediately there would be Bose-Einstein condensation, or Bardeen-Cooper-Schrieffer states, BCS states, or lasing, which I call photon lasing here. Now, I have put this hypothetical overview here just to put things into context and mention all the concepts related to what we are interested in. Don't take the details of this too seriously. It just allows me to introduce these concepts. So if we can vary the electron-hole interaction strength theoretically, and we can vary the cavity quality, and so if we have strong electron-hole interaction, we have excitons, and then in principle we can of course get excitonic Bose-Einstein condensates. Those have actually not really been observed, or they are not well established, I should say. Now, Bose-Einstein condensate, that sounds like a thermal equilibrium concept. In reality, we should probably think about exciton lasers. After all, these cavities, these are open and pumped and dissipative systems with scattering. And so in principle, one should think about exciton lasers. If we have a very high quality cavity instead of excitons, then we form polaritons. These are also bosons and can form Bose-Einstein condensates, and they can also scatter, and we can have bosonic polariton lasers where the polaritons scatter as bosons. Now, we can also have fermionic effects in these cavities, and in particular, we could have fermionic BCS-like polariton lasers. If the interaction strength is basically negligible, we would call this a photon laser. And even the photon laser can be with and without these BCS effects, which I try to clarify in a minute. So the circled region here is what I'm addressing in this talk. Now, this is another overview talk. And so on the far left and on the far right are the concepts that are best established or really well established. So on the far left, I'm showing again the polariton BEC. Now I depict my mirrors as these kind of grayish planes here, just to have a different picture. So here we have excitons that form polaritons, and the excitons can scatter on their center of mass dispersion curve, and that gives bosonic scattering with the possibility of bosonic gain and bosonic stimulated emission, and therefore lasing. These are well established by now. Now, what is of course even more well established for half a century or longer is the laser on the right here. You find this in engineering textbooks. So we have our electrons and holes, they don't interact, and they occupy the conduction and the valence band. And so that's what we call now a photon laser, just to distinguish it from a polariton laser. Now, we are interested mostly in the two categories here in the middle. The polariton state where the electron hole pairs are still bound by the Coulomb interaction, but the binding is not so strong, and that like in the BEC, so this binding looks more and is can be formally related to the original BCS states of Cooper pairs, where you don't have electrons and holes but two electrons. Now, in the photon laser, we could also think about a good enough quality cavity and a strong laser field, and the laser field would then introduce these kinds of gaps that you see here in the band structure, and so we would call them BCS states, because these gaps can be formally or are formally analogous to the BCS theory. Now, let me go back one slide. So we have been working on this polariton BCS state, and this is not all that well established actually. And so I want to talk about our own approach to this, which we did in collaboration with the experimental group of Hui Deng at the University of Michigan. And they had this really nice cavity, which is anisotropic, and which allows us to look actually at this lasing state here with a polarization that is not the same as the lasing state, but we are able to see the distribution, carrier distribution functions that participate in the lasing state. We can just probe those directly, and so that's nice because it allows us to rule out certain possibilities for our experimental interpretation or interpretation of experimental results. And in particular, we were able to rule out polariton BEC from that, because we were able to see a fermionic gain here instead of the bosonic gain. So we were sure from the experiment that we had fermionic gain and therefore no polaritonic VEC. Also, we found that the emission frequency is significantly below the cavity resonance, which is different from the typical photon laser where it is close to the cavity resonance. So we were able to rule out the photon laser. But there's the question of the spectral gap. Now, the BCS theory, the spectral gap is really intrinsically related to the BCS theory, because it's just not there without symmetry breaking. That's different in the BEC case. Now there's also a spectral gap, but it's kind of boring. Of course, there's a spectral gap between if you have excitons or atoms for that matter, if they're in the 1s state or 2s state or 3s state, there's of course gaps between those states, but those gaps are not intrinsically related to the possibility of Bose-Einstein condensation, whereas in the BCS state, the gaps are very, very important. So the question then arose, well, can we actually see those BCS states directly, either in the polariton BCS state or even in the photon laser? So that's our question. Can we observe these gaps in the excitation spectrum directly? And the answer is no, not with optical spectroscopy, but maybe with terahertz spectroscopy. Why is that? So if you think about a cavity here, the laser is circling or bouncing back and forth inside the cavity. And that is related to the fact that the reflection spectrum of this system here has actually a stop band. And so the stop band provides us or prevents us from having a broadband probe here that could actually probe possible gaps in this laser state. So we have to have a probe, a beam that just goes through the cavity and really doesn't care about the mirrors at all. And that is our terahertz. That's where our terahertz beam comes in, because the reflectivity is pretty low and it's pretty much independent of frequency. So that's the basic idea. So the objective of this work is then to establish a theory for terahertz spectroscopy of semiconductor lasers. And in this talk, I will talk only about photon lasers. So I will neglect the Coulomb effects. So basically, I'm back to this slide here. We are looking at this case where we have light-induced gaps that are indicated here, and that I will call delta sub L. And the size of the gap is just basically proportional. It is proportional to the laser field amplitude. So it's conceptually very simple, actually. So we can describe that starting with a Hamiltonian, which has parabolic band structure for electrons and holes, which has the cavity photons, which couples the cavity photons to the interband pair excitation, and then which couples also the classical terahertz field to the intraband electron-electron and hole-hole pair excitations. So then we can write down equations for the interband polarization, creation or annihilation of electron-hole pairs, or the intraband, let me call it distribution function here. So these are density matrix elements, which is an excitation. So the intraband excitation is within one band. We linearize with respect to the terahertz field and then obtain the absorption and other measurable quantities from that. We actually proceed in two ways in our theory. We can write down coupled equations for this interband polarization here in first order in the terahertz field, and the corresponding distribution function, again in first order in the terahertz field. This is somewhat similar to the semiconductor Bloch equation. It's a specific, I leave out the right-hand sides because they are very long, so it's a specific way of solving those equations. It's maybe not the most transparent way, but it's very straightforward. In order to elucidate the connection with BCS states, one can also proceed in this way, and we did this as an alternative. One can use this, what people call Nambu basis approach. We have this 2x2 matrix made up of the interband and intraband functions, and we can diagonalize this 2x2 matrix. And then basically we work, you could say, in a normal mode analysis, or you could call it rest states analysis. Formally, it turns out to be very, very similar to the original BCS theory, actually. at that point. I want to say a little bit, a few words about the terahertz probe in the presence of the laser field, because that is the only kind of tricky issue here, which is not well known, I think. So we have the laser field, we have the terahertz probe, and we want the intraband current that is induced in this system by the terahertz probe. Now the intraband current has two contributions. One is what I would call the laser-assisted terahertz response, and then the Drude response. Now the laser-assisted response, if you like Green's function, you could draw this here in terms of Green's function diagrams for the intraband function. So electron goes from a conduction band to a conduction band state, different conduction band states in general. And so the lowest order term in terms of the terahertz probe would be just shown here. We have nothing else but the terahertz field. I call this a Linhart term. And then we have all these contributions where we have the laser fields included, which are linear in the terahertz, but non-linear in the laser field. And so the task then is to sum up all the combinations of all these diagrams to all orders in the laser field. And so that's basically what gives the response of this system where we have the gaps in the bands as shown here. Now the Linhart function is well known in principle. This is a textbook kind of figure which you find in Mayen's book, for example. If you look at the pair excitation spectrum for intraband excitation, so from one conduction to another conduction band state, if you have a gap in the conduction band as shown here, in the simplest case, or under the most simplifying assumptions, this pair excitation continuum would look like this, and not surprisingly, it would have a gap here corresponding to the gap that you see here. Now, from now on, we focus almost exclusively on vertical transitions in this picture here. So we take Q equals 0, so we go only from one band vertically up to another band, because that is basically most relevant for the optical experiments. Again, this is my cartoon of the spectrum. You can do this a little bit more precisely if you would plot the spectral function of the system. Now that comes from a 2-time Green's function, of course. There you can also see the weights more properly that I indicate typically here with blue and green. They actually just reflect what one would find from the spectral function. Importantly for us, we can look at vertical transitions here and just look at the joint density of states. The most important aspect here is that the joint density of states is 0 below this gap. And so the joint density of states is a direct measure, so to speak, of this light-induced gap, because it's 0 below the gap and non-zero above the gap. Now, one more word about the total measurement. So I mentioned the laser-induced contribution, which is a contribution that sums up all the different K states for the intraband excitations multiplied by the respective intraband matrix element. There is another term that I mentioned briefly, is the Drude term, which is this kind of textbook example of 1 over omega dependence, has a certain Drude damping, which we put in phenomenologically. And unfortunately, at small omega, this guy unfortunately contributes and has a tendency to swamp everything. So the results shown below are therefore in a kind of two-pronged approach. First, I want to use very, very small Drude damping, just in order to establish that in the idealized case, we can clarify the physics and we can clarify signature of these BCS-like gaps. And then later, I will make the Drude damping a little bit more realistic to see what we can actually offer experimentalists to look for, what is more realistic to be expected. Now, the basic idea is now that we look for features in the terahertz absorption, and these features, minimum or maximum, should grow as the laser gets stronger. And so in the first part, I have a laser model here, laser pump model, sorry, I'm forgetting the L here, which has a certain pump rate and a pump distribution. And in the first part here, I just want to vary the pump rate, and that makes the laser stronger, or if I want the laser stronger, and corresponding the gap larger. So let me therefore present numerical results now. So there's a bunch of curves here. Let's start out with the upper left here. The upper left shows the joint density of states. As I mentioned before, it's 0 below the gap. And we are showing here 4 curves for 4 different laser strengths, by which I mean, in this case, I just vary the pump rate. The pump rate legend is shown here for the 4 different colors. So you see the gap gets larger and larger and larger if I increase my pump rate. Now the question is, how does it show up in the laser, in the terahertz measurement? So the experimentalists can measure the absorption, for example, which is shown here, and correspondingly the absorption is just proportional to the real part of the conductivity, which is shown just above. And you see immediately that there are minima here in the absorption, and the minima, they track the gap. So the minima go further to the right. So this is as a function of frequency. They are at larger frequencies if the gap is larger. So the minima, in other words, provide a signature of this light-induced gap. You could see this also in transmission, as shown here, but reflectivity would not be very appropriate for this kind of measurement. Now, this is just a summary plot. So here we plot as a function of our pump rate of the laser. We plot the minimum that we just read off the plots on the previous slides, and we plot also the BCS-like gap size again as a function of the pump rate, and we see they track very well. So we can conclude that at least at sufficiently small Drude damping, the absorption minimum is a signature of the BCS-like gap. I want to make one more comment about this figure, because I kind of rushed over this and didn't point out one important aspect. This is showing absorption, and here's 0. So the minimum actually was at negative absorption. It's actually a maximum, if you will, of the gain. We find gain here, terahertz gain in the system, and so this is at least surprising to us. It was surprising to us initially, and so this is a consequence of this wave mixing that I pointed out before between the laser field and the terahertz field. Now, the wave mixing does not always provide gain. It depends on which k value you're looking at. So if you are looking at k values close to k equals 0, it's actually absorption. At k vectors larger than this minimum here, where the gap actually is, we find gain. And so we can analyze it in our numerical simulation more closely, as shown here. So this is this intra-band distribution function. And so we have absorption here and gain here. And at the end of the day, we have to sum over all k states. And so then it turns out that because the terahertz matrix element is proportional to k, it gives a bigger weight on the gain than the absorption. And that, in essence, then gives us the gain that we see in the overall absorption here shown on the left. So that is not so intuitively clear, not as intuitively clear as, for example, a regular laser. Let me comment really quickly that we made sure, of course, this gain vanishes if we are in a quasi-thermal equilibrium. These figures show quasi-thermal equilibrium, same kind of plot. We see there's no sign change here, no matter how we change the density, or in this case, the quasi-chemical potential. If we vary this pump density, which is more similar to what an experimentalist would actually do, the situation is not quite as nice, but it's still sufficiently good, I think. So here, varying the pump density means that the minimum gets closer and closer together, and also the BCS gap gets closer and closer together. In other words, it saturates as a function of the pump density more easily, and the tracking is I mean, it is still there, but maybe not quite as nice as if one could vary the pump rate. Also want to talk about increasing the Drude damping, because that, of course, in the experiment, that is not so easy to change, I assume. So this shows the curves again, basically the absorption curve here as a function of frequency for various Drude dampings. Let's just focus on the purple curve here, where we chose a relatively, I would say, in our scale here, large Drude damping. It may still be smaller than in most experiments. We don't see any clear signature if we just look at the absorption. But if we would take the second frequency derivative, then we see a clear signature here. For comparison, again, is plotted the density of states, which just shows that the gap in this case is exactly here. And if you look at the second derivative, there's a clear signature related to the BCS-like gap. Also, I should mention that, of course, if the Drude damping gets large, well, there's no Terahertz gain anymore. So in order to see the Terahertz gain, you really have to have a way to make the Drude damping small. It would be nice to have more research, to have more insight into that, but in the future. So let me see, I have 1 minute left. This is my last slide here. If you don't have a laser, as shown here, I've talked about the laser all the time. If you just have a quantum well and an external optical pump, this scenario has been pointed out in 1969 here, published in English, and in 1970, and it has been pointed out that this actually is a model for what we call now BCS theory. These people didn't refer to Vadim Kupashiva. They refer to Russian literature, of course, to Bogolyubov, very early papers, and Kosov. And so I'd like to call these Kalitzky-Elesian gaps. These are just the same kind of gaps, but not brought about due to spontaneous symmetry breaking, but brought about due to an external pump, as shown here. And so everything you do with a laser, you can also do with an externally pumped quantum well, and that's just spectral hole burning then. I'm running out of time here. Let me summarize briefly and focus on the three items here shown in yellow. So we found that for small Drude damping, the extremum in the terahertz absorption does indeed, as we had hoped, check the BCS-like gaps, at least in the case of photon lasers right now. We found that at larger Drude damping, the second frequency derivatives is good enough to show the signatures of the BCS-like gap, frequency derivative of the absorption, I should say. And we found that for small Drude damping, terahertz absorption is negative, so we obtain gain, actually. And here are 3 references that are related to this work. And I'm looking forward to questions.
Thank you very much, Rolf. Questions, please. Rolf. Robert, please.
Yes, I have a question on the very nice results there, and I have a question on the shape of that, absorption that you're showing with a minimum. I understand some of it is, I guess, due to, if I understand correctly, due to the band structure that is light induced.
Yes.
In the BCS connectivity absorption, there's also this effect of the coherence factors. So I'm wondering if there is something similar here that applies in terms of the matrix elements, coherence factors, or the factors before the annihilation and creation operators.
Let me see. When you talk about matrix elements, you mean the matrix elements in the Hamiltonian, the in-char-band matrix elements?
I think for the BCS, it's essentially basically for the coupling of in that case the light field, and then you get these coherence factors due to the U and V's in the BCS.
The U and V's they came out if you do this what we call the Nambu basis approach. You actually see the U and V's on the right hand side. There's lots of terms there at plus the gap and minus the gap, and at 0 frequency, 0 terahertz frequency, and all these terms are superposed in the results, and all these terms have to be summed over k. That's why I cannot give a very, very simple simple explanation for every detail of those curves. But yeah, we can check down for each k state. It's easy to see all these u's and v's. Okay, but this is a sum over k, and that makes the interpretation a little bit more tricky. but the identification of these Bogoliubov Bogoliubov transformation, that is we just wrote this in the paper, and that is straightforward to do actually. Yes, that's correct. Yes.
Yeah, because I have this picture of the metastability theory, you know, where you have for the absorption of the BCS superconductor, where you have you don't get the density of states as the absorption, but you get this suppressed onset at the gap energy due to this coherence factor interference, basically in the absorption.
Yeah, I mean that is basically. I mean, here we have the Drude term that contributes here, yeah. and then this absorption is one of the terms that we get in this where was it now? In this approach. It's of course also there in this other, but here it's readily identifiable.
Thank you very much. Thank you, Rolf. And our next